Hello. So me and my colleague, like I said, Damien Makuc, will have these exercises, and I hope that we will be able to tell you a little bit about NMR in liquid. So as you will see, we have prepared few examples on small molecules, and also we can see some spectra of larger DNA and protein molecules if we will have time. But first, I will do some short introduction, and I hope that I know that something you already heard in the morning. So maybe we will just quickly repeat some things that you will be more familiar later with NMR spectra. So okay, just to tell you a little bit about this, we come from Slovenian NMR Center. And this is institute facility, and we are also national research infrastructure, which can be used both from academic and industrial users. And we are also center of excellence, and we are, as you know, we are also partner facility of CERIC. So our equipment can be used also through CERIC. If you will, in the future, if you would like to use our equipment as well as expertise. So our NMR facility, we want that our equipment is up to date as well as expertise. So in our NMR center at the moment, we have 6 NMR spectrometers, and 5 of them is mostly for liquid state NMR, and 1, this magic, is for solid state. And the most powerful one is this so-called David. Each NMR spectrometer has its own name, so we know on which one we are working. So David, this is the most powerful one, 800. And then we have Aska and Lara, which are 600. And both these 3 are equipped with a cryoprobe, which means that this electronic of the probe is also cooled with liquid helium. And due to that, the signal to noise ratio in the spectra are much better. And this means that you can use those NMR machines if you have low amount of samples, or if you want to acquire as quick as possible NMR spectra, which you need for structural elucidation. And then we have also Oro and Nika. This is 600 and 400, and they're mainly used for routine measurements and to check, let's say, products of the synthesis and so on. And this Nika can also be used for liquid as well as for solid state. So we can do both measurements on this spectrometer. So these magnets, it is very important how it looks like. This is a magnet, how it looks like inside. So we can see here it's a coil where we have this magnetic field, and this coil is inside the helium, liquid helium, which is, I think, at approximately 4 kelvins. And around that, it's liquid nitrogen, which is cheaper, and also it's that liquid helium evaporation, it's not so quick. So from time to time, we need to feel this, that NMR spectrometers works like they should do. Okay. With NMR, the problem we want to solve by NMR, of course, at the end, we want to get a structure as well as dynamic of the structure at the atomic level. And what we really see is this Nmr tube, yeah. And inside the Nmr tube, we have some sample, let's say from small organic compound up to large macromolecules like DNA, RNA, or proteins. And by the use of NMR, like I mentioned, we want to see at the end how these molecules which are inside looks like. 2 most useful nuclei, let's say for organic chemists, are proton, this is 1H, and 13C carbon. And it's really nice to work with them because both they have spin 1/2, and these elements with spin 1/2 gives the nicest signals, the sharpest signals in NMR spectra. And another important thing is also natural abundance. And in the case of proton, this 1H, we call it proton, the natural abundance almost 100%. And in the case of 13C, because 13C is NMR active nuclei, this is in the natural abundance is only 1.1%, because in the nature the most abundant is 12C, but this one is NMR not active. So due to that, if you want to acquire proton NMR, this will take few minutes, but in the case of carbon, you need a little bit more of time. So this is Nmr Periodic Table. Such tables you can find on internet. And here are some elements which can be measured by NMR. And as I mentioned, these NMR active elements with nuclear spin 1/2 are, let's say, protons, then carbon 13, nitrogen 15, fluorine 19, and phosphorus 31. And these are all elements which are very important in biological and chemical structural elucidation. And this has all spin 1/2. And then we have two elements already mentioned before, carbon 12 and O16. This is oxygen 16. And this one has this nuclear spin 0, and this one are not NMR active. So in the case, if you want to measure oxygen, you should measure oxygen 17, for instance. You can see it here, oxygen 17, which has a spin 5/2. It's NMR active and you can measure it. But the problem is that you should prepare your molecule already that oxygen 17 is inside the molecule. And then we have also this quadruple nuclei like 14 nitrogen, this is deuterium, boron, and so on. And like I mentioned, for instance, if we take a look, I already mentioned that for carbon 13, in that natural abundance is approximately 1.1%. And in the case of nitrogen 15, the natural abundance is 0.37%. And this means in the case if you want to, for instance, make a 3D structure of some larger proteins, that these proteins should be 13C or 15N labeled. So already from the beginning, when the synthesis of the protein is done, you should include inside these two elements which will enable determination by NMR, the structural determination by NMR. And okay, this is in the case of liquid, I already mentioned, this is Nmr Tube. And this Nmr Tube, we put it in this so-called spinner. And you can see this is the sample. Approximately we used in the regular tubes, we used 500 to 600 microliters of sample. And the usual concentration for, let's say, for biological molecules, it's from 0.1 to 1 millimolar. And in the case of smaller organic compounds, we usually put few milligrams of samples inside. And as you will see later, all this for this solvent, we always use some deuterated solvent because deuterium is important for NMR measurements. So the solvents should be deuterated, like D2O, then deuterated chloroform, DMSO, and so on. And then this all together is put inside the magnet here, and then the measurements are performed. Yeah? And in this case, here it's presentation of one proton NMR. And for this compound, this is ethanol. And as you can see, we observed not free signals, but signals at different positions. And you can see that already from chemical shifts, what is important in NMR? First, the chemical shift of the signals. So you can see it here that, let's say these free signals are at 1 ppm, and these 4 signals are between 3 and 4 ppm, and this one, it's a little bit less than 5 ppm. So chemical shifts already tells you about the nature of the protons in the molecule. And then the next thing, but this, when we will do the exercises with Mastranova, you will see how this works. And then the next important thing is signal intensity. So if we integrate these signals, you can get the ratio of the protons. So these 3 signals should integrate, let's say, for 3, because they belong to these 3 protons here. And these 4 signals should integrate for 2, because they belong to those 2 protons. And this one should integrate for 1, because belongs to this proton here. And another thing is this scalar coupling. Because you can see that for these signals, we don't see only one signal, but we see a triplet. We call it a triplet. And this means that the shape of the signals tells you how many protons it's on the neighboring, let's say, carbon atoms. But this I will explain it in the next slides. You will see it. So, okay, I think that you already heard talks about solid state NMR, so we can do liquid as well as solids. But these exercises today are for liquid state NMR. Okay, this is proton chemical shift range. And this proton chemical shift range is, here it's from 0 ppm up to 12 ppm. Some signals can be also observed up to 20 ppm, but these are mainly for protons which are involved in hydrogen bonds. And already from chemical shifts, like I mentioned before, we can say a lot about the nature of the protons which are in the molecule. For instance, aromatic protons, they will resonate in this region here. In this region here, aliphatic protons will resonate here. Here we have, let's say, some aldehyde protons, this one in this region, and here protons of carboxylic acids are here. So when you see the spectrum and you see signals at certain chemical shifts, you can already say, these protons belongs, for instance, to aromatic protons, and so on. And already also, if we are working with larger molecules, such as DNA, we have also some specific regions for protons which can tell you a lot about base pairings in the molecule. So for instance, if we have a DNA molecule, which is double helix, bDNA, and for instance, for these GC base pairs where guanines are in base pair with cytosine, you can see that this proton here, which is on this nitrogen, is now in hydrogen bond with this nitrogen of the cytosine. And the chemical shifts of these protons are around 13 ppms. So if we see the signals around 30 ppms, and we know that we have inside bDNA structure, we can say, those signals belongs to these protons of GC base pairs. And in this, here, maybe I should also mention that the protons which are on nitrogen or on oxygen, they can exchange with the protons from the solvent. So if they are not involved in hydrogen bonds, like here, you will not see them in NMR spectra. But the protons which are on carbons, they are usually not exchanging with protons from solvent. And in this case, if we have, for instance, CC base pairs, you can see that this proton here, which is also involved in this hydrogen bond with this nitrogen here, this proton will resonate here at a little bit more than 15 ppms. So okay, if we see these signals in the spectrum, we can say, okay, we have these such base pairs. Most likely, we have such base pairs in the structure. And this is another possibility how DNA can form different motifs. This is so-called G quartet. And in this case, these iminoprotons here, these NH, we call them iminoprotons, are also involved in hydrogen bonds, but in such arrangement, they will resonate at this chemical shift. So from here, from this slide, I just wanted to say that chemical shifts can tell you a lot in small molecules as well as in larger molecules like DNA and so on. Okay. And now we can go to this coupling constant. So if we have such cases here, that this is a proton, and on neighboring, we don't have on neighboring carbons or elements, we don't have any other protons. And this proton will look like in NMR spectrum as a single as one signal. And if we have such a case that this proton here, and on the neighboring carbon, we have this another proton. This proton will not give any more a singlet in NMR spectrum, but it will be a doublet due to this proton here. So we will see two such signals, and these two signals will indicate that this will be, both signals will be for this proton here. And in the case if this proton has two protons on neighboring carbon and they are not equivalent, we will see so-called doublet of doublets, so 4 signals, and so on. And also you can see that there is a distance between those, let's say if there is a splitting, there is also so-called, there is a distance in Hertz, which we called it a coupling constant. And already from this, we can say something about the structure. If we have this case, for instance, one proton here, and another one is on the other side of the molecule, so-called in trans conformation, this splitting will be from 12 to 18 Hertz. And in this case, where they are both on the same side, so-called cis conformation, the splitting will be lower from 7 to 12 Hertz. So you can see it that from splitting, you can also say something about the structure. And this here I showed you how it's with proton NMR, and now we can continue with carbon NMR, which is also very important NMR spectrum, NMR experiment. So also in the case of carbon, if you take a look this molecule, for instance, we got this carbon NMR spectrum, and you can already see that the chemical shifts in the case of protons were much narrower, were between 0 and 20 ppm, while here the chemical shift ranges from 0 up to 200 or even more ppms. So this is the signal from the solvent, from chloroform. And then we have in this molecule, you can see that we have 1, 2, 3, 4, 5 carbon atoms, and each signal belongs to one carbon atom. And when we do assignment, we exactly know, this signal belongs to this carbon, this one to this one, and here, and so on. But how we do that, we will see later when we will assign some molecules, using also 2D experiments and so on. And also in the case of carbon chemical shift, you can see that there are some tables, and which explains you also, like in the case of protons, if you see, for instance, these carbon signals, let's say in this region between 100 and 150 approximately, you can say, more likely these signals belong to aromatic carbon atoms. And in this, here in this region, you can see signals which belong to, most likely to aliphatic carbon atoms. And here, the signals which belongs to carbon atoms of ketones, aldehydes, and so on. So like in proton, also here, you should remember that the chemical shifts tells you a lot about the nature of the carbon atom. And now we will go just quickly through some 2D NMR, which are very important for structural elucidation of smaller compounds as well as of bigger one. And the first one is so-called Cosy correlation spectroscopy. I know that in the morning you already talked about a little bit about these experiments. So in the case of Cosy, we observe the correlations through bonds. Let's say this proton is 3 bonds apart to this one. So it will give signals in the spectrum. So if you take a look this Cosy, you can see here it's a proton dimension and also a proton because it's homonuclear NMR experiment. And here it's a diagonal, which is proton NMR spectrum. And these signals, these so-called cross peaks, are important to say something about the structure. And if you take a look, let's say this CH2 group marked with number 5, the signal in the proton will be here. When you do assignment, of course, you know it here. And this signal, you can see it here, it correlates to protons marked with 6, you can see. So because it's a neighboring proton, there are 3 bonds apart. And as well, this signal should correlate also these protons here marked with 4. So here and here. So we can see these signals, and these signals are due to these correlations between protons marked with 5 and 4, and so on. And when you figure it out what all these signals are, you can construct also based on some other experiments the final structure. And the other one is TOXI, which is so-called total correlation spectroscopy. And in this case, depending on the mixing time, we will also see later in the exercises how mixing time of the toxic can influence how far we can see the signals. If the mixing time is, let's say, long enough, this proton can correlate to all these signals in the same spinning system. So, for instance, if we take a look, this CH marked with 4, this is this one, and this signal will see signal for this 7. It's up here. Then it will see this 6 and also this 5. So this signal will correlate to all these protons here. Yeah. So another one is nosy, which is also very important also in the case of structural elucidation of larger biomacromolecules. And here we don't connect the protons through bonds, but here we connect the protons through space. So if there are 2 protons close in space, then we will see signals outside the diagonal. Diagonal again is a normal proton NMR spectrum. And the protons, for instance, can be many bonds away, but in the space, if they are up to, I think, 5 angstrom away, you can see the peak between 2 protons which are close in space. So the next one, which is also very important, it is HSQC. And this is heteronuclear single quantum correlation spectroscopy. And here in one dimension, we have proton. And in the second dimension, we have some heteronuclei. And in this case, carbon, we can also have nitrogen. And in this case, these cross peaks, which are in the spectrum, they correlate protons directly to carbons through one bond. So you know exactly, this proton, let's say, these protons here are connected through one bond to these protons here. So this is very useful experiment, and we will also see how it works later. And another one, and the last one in this series of these 2D experiments is heteronuclear multiple bond correlation spectroscopy, Hmbc. And here we correlate protons not to its own carbon, but to the neighboring carbons. So we can take a look at the usefulness of these experiments on this compound. And we can see that the proton here, here it's a proton at position 8 at this carbon, which is here. This is the proton. And these protons give signals to this carbon here, then to this carbon here, then to this carbon here, and here, this, and as well as here. So this proton gives correlations to all carbons which are close through bonds. And when you assign all this, you can, at the end, you can set up how the molecule will look like. So, okay. Now a little bit about what we will do when we'll do exercises. We will use this Mestre Nova program. And first we will do some processing. And originally we get this so-called feed free induction decay, and then you can use some Fourier transform to get this time-dependent, frequency-dependent. From time-dependent, you get frequency-dependent NMR spectrum. And this feed, you can see it, this feed, we can play a little bit with this. And because the first part of the feed, there is mostly information about the signals. And the last part of the feed, it's mostly information about the noise. So we can multiply this feed with some function, for instance, with exponential function, and we can get, for instance, less noise. But we should be careful because at the same time, if you use this exponential function, we can get also broader peak. But this you will see how it works in on real NMR spectrum. So you can play a little bit to get better, that the spectrum will look much better, yeah. And we have different function from exponential, Gaussian, sign bell, shifted sign bell. But in the case of Proton NMR, we usually use exponential or in combination with Gaussian. Then we will do, like I mentioned, we will do this Fourier transform, and then we will play a little bit with phase correction, so baseline correction, and then we will do analysis of the spectra. We will set up the reference. This is very important because you want to have that the signals of your compound are the right chemical shifts. And usually we set up the reference on, let's say, you can set it up to solvent signal or to some reference, which is some internal reference like TMS and so on. And then we will do integration to see how many protons it's under each peak. Then we will do peak picking and multiplet analysis and so on. And also in the case of 2D, this was before for 1D NMR, but in the case of 2D, you also do processing first in one dimension and then in the second dimension. But this program, which will be used, it does a lot of this processing already for you, so it's very useful, friendly. But if you are not satisfied, you can also do manually. We will see it. And these are just examples which we will go through. So we will see how far we will come. First, we will start with very small molecule with very, and we will see how this spectrum will look like, and we will try to figure it out what this molecule from this empirical formula, what this molecule is based on NMR spectra. And then we will continue with assignment of ibuprofen. I think you all know this molecule. This is some drug molecule used for if you have some pains. And then we will continue with adenosine. And this is a building block of, let's say, for instance, of DNA molecules or RNA molecules. And then if you will have time, we will just take a look Proton NMR of some G quadruplex structure that you can see how many protons, how many signals you can get in this case. And then if you will get time, I just wanted to show you how this sequential walk, I know that you heard already in the morning about sequential walk. So we will see how this sequential walk can be determined from nosy NMR. And then here I just presented about the proteins, how, for instance, ubiquitin, which is not so huge protein, it's 76 amino acids. Here, how it looks like a proton NMR, but for proteins, this fingerprint, like in small molecules, it's not usually a proton one-dimensional NMR spectrum, but it is usually this nitrogen HSQC. And if you get nice dispersion of the signals in this type of experiment, you can say, this protein it's structured. But in the case if these signals are not nicely dispersed, then you know, okay, this protein is it's not nicely structured. Maybe it's some random coil or so, or something like that. And at the end, I think we will not have time, but at the end, here it's one antibiotic, azithromycin, and you also got all these NMR spectra. So if you will be willing, you can also do assignment by yourself, or you can ask us if you will not be able to do it, you can do it by yourself later on. So with that, I finished. Now I will do stop sharing, and with one of my colleagues, we also prepared a movie, how we prepared a sample and how we measure proton NMR. So before we start with exercise on this Mestranova, I would just like to show you this movie, just to find it. Okay, DNA synthesizer, yeah. So with that we prepare NMR sample. And there is equipment with which we purify it later on, the NMR samples. And here is Simon, who is now preparing and centrifuging the NMR sample, yeah. For sample purification, we also use FPLC as well as HPLC. To measure absorbance of DNA or RNA oligonucleotides, we use UV spectroscopy. As well as we also use UV spectroscopy to measure melting temperatures. This is D2O. Yeah.
Okay, so now we have to transfer the sample into the Nmr tube. So we'll use this plastic pipette, which is thin enough to go into the Nmr tube. Okay. So.
And here is approximately how much? 500?
This is 600 microliters. Okay, and we put on the cap, and now it's ready for the spectrometer.
Так, сам звук.
Okay.
And now the sample will go inside the magnet. One of the samples was already in, yeah?
Yeah.
Okay, this one came. And now our sample will go into the magnet. Number one.
Okay, so the sample is now inside, so the first thing we have to do is log the spectrometer to the deuterium frequency. So we have a mixture of H2O and D2O, and we also have some salt in our sample, so we will choose this. Okay, and now we have to wait for the spectrometer to log the frequency.
Maybe we can open this log.
This is the log signal display. Here you can see.
And due to that, it is important, yeah, that we have solvent with deuterium in the Nmr tube, yeah, due to the log signal. And Nmr, as we can see here, this sample will be measured at 25 degrees. Yeah? But we can measure the samples, let's say from below, we can go even below 0 and up to 100 or even more degrees.
Okay, so now as you can see here, it is done with the locking of the spectrometer. So what we need to do next is tune it. So we use this command, automatic tuning and matching.
And now we will tune it only for protons frequency, yeah, because we will measure proton Nmr. And in the case if you also want to measure carbon or some 2D experiments, you also need to tune it, the carbons.
Okay, so
this is done, yeah.
Now we need to shim.
And with shimming, we homogenize the magnetic field, yeah, so that the signals will look, in the case if there is a singlet, it should look like a singlet and not like a doublet. So and this can take a while, yeah? A few minutes or...
Yeah, it depends on the sample. Sometimes it's quick, sometimes it takes a bit. But it is finished now. So what we do now is calibrate the pulses.
This is a 90-degree pulse for proton, yeah? Okay, the pulse calibration is now done, yeah?
So now we need to set the gain, the receiver gain.
And this we need to set up as high as possible, yeah, to get good signal to noise ratio.
Okay. And now we go to the acquisition parameters and we can change some parameters. For instance, change the number of dummy scans and we will put here 8. Change the number of scans and we will put here 64. We can change the sweep. So for instance, we want 20 ppm to be recorded. So we can change this. You can see here how long the acquisition time is. So for each scan it is 1 second, a bit more. And that is actually...
A delay, D1.
Yeah, we can change the delay, which is now here 2 seconds, which is okay. So what we can do is check the experiment time. So we can write XT. It will tell us, okay, the whole experiment will run for 3 minutes and 40 seconds. And now if you want to run the experiment, we write ZG to go, and now it is starting to record.
Okay. Now the experiment is finished. We can see the result, and with this now we need to phase the spectrum so that we will get all the signals on one side. This looks like nice. This is a Proton Nmr Spectrum of one of DNA oligonucleotide. And here on the left we can see the signals of immunoprotons. These are NH protons. And on the right we can see aromatic signals which belongs to aromatic protons of DNA nucleotides. So yeah, do you hear me?
Yes, we can hear you.
Okay. With that, now we will move to our exercises using this Nmr Nova program. I hope that everybody were able to download it, and also the Nmr Spectra, which we gave it to you, so that you will be able to use them now. So now I think my colleague Damian will start to share his screen. And together with him, we will start with first exercise. And you also have it on these slides, which I gave it to you. And in between, if you have any question how to do something, just interrupt us. You know, if you want, okay, why you are doing this, how you should do it, or I have some problems with it, and so on. Just interrupt us in between. Yeah. Okay. Do you also have on your screen? Do you open also Nmr Nova on your screens?
Yes.
Okay. So yeah, now we will go to the first example, which is this C4H10 O oxygen, and also in these slides, which I gave it to you on page 25, I already did some calculations of this index of hydrogen deficiency. And this index, you can see also the formula, which is 1/2 of the, you should put inside the number of carbon atoms, then the number of nitrogens, protons, and X is heteronucleus. And if you calculate this, you can get the index for this molecule 0. And if it's 0, this means that there is no ring or no double bonds. In the case, for instance, if it would be 1, it would mean that there is one double bond or a ring in the molecule. And for instance, in the case of 4, if this index would come 4, it would mean that we are dealing with some benzyl ring. So yeah, first, so now we will go to just Damian, go to this file open.
Yeah, hello there. Also from my side, yeah, I will also help with Primož you to process this data and see what we can do. If at some point it will be too fast, just let us know, maybe with some comment in chat, or you can speak up. I will try to do it slowly, at least in the beginning, but yeah, in case it's too fast, just let us know. Yeah, we can open the data here from the menu, this one, so file open, or you can use shortcut or just pull file directly from Explorer or Finder, whichever you use, and drag it to the Nmr software. So the one that is easiest for you will work just fine. Let me see. So we will start with this first exercise. And here we have a list of spectra, and we will use, let's go with Proton first, and then we'll do open. I'll just first open all the data, so it's then easier then to process or to analyze when we have it opened. So I'll do it consecutively. So we have proton, carbon. We can check also this depth, 135. This is useful.
And HSQC.
HSQC.
Yeah.
Okay. So we have more of them, but this 4 will do for now, I think. We have something in chat. Aha. Someone is missing files. Can you, Primož, can you explain? Did they get them mail or something? I think you're muted, or did you unmute this? Or maybe we can do now just short break and like 5-10 minutes, so everyone can get the data, if not, and they can follow easy. Or what do you suggest?
Yeah, if you want to download your Spectra. Diamond, can you repeat it?
Okay, so we are, wherever you have this data downloaded. So I have it here. It depends. I mean, this depends on your software, but yeah, I have like this folder with 7 of these folders inside. So this is the first one that we are doing now. So the one with number 1 and this formula, and then the files here are this BMSC and then zip files. So this is one version how they were compressed, but this can be opened directly then with Nmr. So the first one that I opened was this Proton, so BSME 0004471H. This one, then I opened also Carbon, and the one shown here, and then this depth 135, and the last one I opened HSQC. We have several more, but for now these 4 should be enough, and they are opened like this here. So we have all these 4 spectra, and the one that is selected, this now is HSQC, but we will start with Proton. So we click then here to the first one, and here is the Proton as it is opened by Nmr initially.
I get message and no format of file for the zip.
Okay, so can we proceed or?
I try to open zip.
I guess we can go on, huh?
I got message and no format.
No format.
Hmm?
You have now Spectra or not?
I have downloaded the Spectras.
Yeah. Aha, thus opening the zip files directly works well with Nmr Nova. Yeah, yeah.
Yes, that's true.
Okay.
Yeah. So you can open directly. You can also pull from Explorer, pull the files also to, I mean, drag and drop to Nmr Nova. It works the same way. It will just open it there. So the software is really easy. I mean, really easy or user-friendly to use.
Okay. And now maybe, Damien, in this spectrum, maybe you can show us just how it looks like the fit for induction decay, because when you are using this Nmr Nova, you can directly, if you open the Spectra, the file, you can directly see the Spectra because it's very user friendly, like I mentioned before. But now we will go step by step what are the real data and how you do the Fourier transform and how we can play with this apodization and so on. That you will see it.
They here also files, so you can somebody share it already if you don't have it. Yeah, so when you open, as also Primož said, it's already processed, but let's go one step back. So here at the top, you have different icons, and they are ordered quite, let's say, intuitively. So we will start with this FT1 here. Click here now. So if we go to, if we choose now original FID, we will get the image. We should get the image, I hope. So why it's not working? This is strange. I don't know if it's so slow or something. This should be quite fast. I don't know. Yeah, so this now is FID, so this free induction decay, the spectrum like from raw data. So this is the signal that we get from the probe or from the spectrometer, and that is recorded. So this is our initial information, and then the next step is to do this FT or Fourier transform, and this will now change the data points from time dimension to a frequency dimension. So the scale here is in seconds, and then when we do this FT, so spectrum after first Fourier transformation, it will transform this data to the spectrum, to frequency domain. It's a bit strange. It works that slow because I still see FID.
And on your computer is also only FID. On your computer, you have also just FID, huh?
Yeah. I'm just switching between 1 and 2. I'm not sure what's happening. Yeah, no, it's maybe it's some bug or something. I'm not sure because usually it works fine. Okay, and then yeah, when we do this FT or Fourier transformation, we should see the spectrum like it is here now. Then the next icon that you can see here is about apodization. So Primož briefly, okay, let's check what is in the chat. Problem with importing files. Okay, so importing files, you should they cannot import. So one way would be, I'll try to drag, can drag, and now we have this Proton. I just drag and drop from the Explorer or Finder in the case of Mac, and it should work. So I have two the same. The other one, it's like just file open, then you have to find where your data is, and you open or import directly these zip files. So this compressed data, it's like one file, and you click open. So I hope you can figure it out. We all have problems. But what kind of problem do you have?
What helped? Hi, Martin Chebesta. What helped me is that I unzipped files to the folder, and then it worked. And just dragging the folder to the program worked. So I think this is a workaround.
The first one is folder.
Then just unzip the whole folder, yeah, the whole exercise NMR folder.
Yeah, maybe you have to unzip it. Let's. Yeah, it's a bit strange. So when you download your data or this data, you will have probably it will be all together in one zip file, and then you have like 7 different folders. So one which are beginning with numbers 1, 2, and through 7. So in this folder, it's another folder with just I'm showing it now. So it's just folder with this molecular formula, and then in this one you have files that are shown here in the last column. So you have to open these files here, this BSME and so on. Yeah, the file that you download, you have to probably, it depends how it's downloaded. Maybe you have to unzip it, or because it's one folder, yeah, it's one file, so you have to unzip and uncompress it. So, did you succeed? Okay, it seems it works for most of people. So I hope you can catch with us. I'm just waiting, or we can go on. Maybe we proceed. Primož.
Yeah, we can continue. Yeah, so with this NMR,
I hope you can follow. So we will continue, and yeah, this is also recorded, so you can maybe even rewatch later if you need. It's okay. We can. I hope we can go on.
So Daniel,
Okay, it's more people that are having problems.
But maybe it's with this, they should unzip it first. So maybe this is the
problem. You have to unzip and have multiple folders.
But the main folder, no?
This the main one.
Yeah.
You don't have to unzip this other. I mean, this spectra that are then listed there.
No,
this you just drag or open directly with Mestronoa software.
Yeah, so maybe Darren, we can continue to set up the reference and maybe, or just to show if you will be able to do this, how we do baseline correction, phase correction, and so on.
We will follow these icons in the same order that are here, and we will see all these things. So I wanted to start with this apodization. Primož introduced briefly earlier. So we have with apodization, we can use different filters on this FID, and this will show us data in different way. I mean, it will change our data a bit. As you can see, at least now I have it set this exponential function to 1 Hertz. This means that if you remember the slide from earlier, that your FID will be multiplied by exponential function, and this will affect the signal to noise ratio and the resolution of spectra in different ways. We will, I will maybe switch now to zoom in one of these signals. So for zooming, you can use the icons here at the top. You can see zoom in, the first one, or you can use Z. This is like shortcut. So you just press Z, and then this cursor will turn into this zoom icon. So if I roll over and drag over the peak, it will zoom in this region. So here is one of our signals. And what I wanted to show with this apodization is, so we have now it set to 1 Hertz, and we said it before. If we make it like higher value, so if we increase the value of this exponential function, let's say to 5, you will see it changes the signal. So what we have now here is our resolution is worse because we don't have these sharp signals that we saw before, but we improved our signal to noise ratio. At this point, it's a bit harder to see. I will just I cancel it. Sorry. So let's go. Yeah, okay. I will just move this higher, so we will see what happens at the bottom. So this is now at LV, or this exponential 1. So if we do it like 5 before, so what we can see, this noise that we have at the bottom of the baseline is reduced. So in a way, with higher value, we can improve signal to noise ratio. Of course, when we have this type of compound or sample like here, so it's really high, quite high concentration, we usually don't need that much improvement. But just in some cases, it can be really important that we set the best option for the processing. So you can see here we have a bit of this noise with this 1 Hertz value. If we have it to 5, this line here is much more smooth.
And I mean, maybe just put it on 0, yeah, to see how it looks with zero,
You can
with
start
no.
with 0, yeah. So this means no changes. Yeah, this is maybe also a good example. So if you have 0, so this means no exponential function is used. So this is like raw data of our spectrum. So we have a noisy baseline here in this region, and then yeah, of course, we still see the signal. So with this value, we can see that resolution is really good. So we have like really well resolved signals of this multiplet, which is triplet. Okay, we have some comments in chat. Let's check. Okay, yeah, you can also unzip. Let me see. If you will unzip even further, I think the FID is the file that you have to use. Let's see if we have it also in this one. I'll just use it once more. So yeah, here I uncompressed this Proton zip file, and it is now shown here. So we have it. This is unzipped. If you use this option, I think you can open this FID file. So if I do it now, it should work. So I have it now here at this slide 7. So this is the Proton that I opened. So FID, because the FID means this free induction decay that we examined earlier. So this is the date of this is your actual data. The other files are like parameters and so on. And this FID is the one that is used. P data is the one that has, this is like processed data. But if you want like, let's say, really raw data, so your initial is this FID. So you can also open this one.
But I mean, also in the case of P data, you can open it, this 1R file, yeah?
1R.
1R, yeah, just try it.
Yeah, it's a lot of options.
Yeah, so you can also do that.
Same. From the image, I didn't open the image. Yeah, you can, from the image that you shared, you can choose 1R also, or this FID that was before. FID is your raw data. P data folder, it's usually processed data, but in general, it will copy this data. So 1R is like processed data, and it's copy of your data. So this is the way it's done in, I think it's from Bruker format. So it will, when you process it and save it, it will just add more data, and usually it will have quite large files if you do multiple processing. So I guess we can go back to our spectra. This part that we played a bit with apodization. So yeah, you can use really high value. I can exaggerate here to put it to 100. Yeah, but I didn't click OK. So you will see, you will get really one broad signal. It's even not showed properly, I guess. Even I have some problems. Okay, this is now 20. So if you put really high number here, you will get just one broad signal. So you don't see multiplicity and so on. So don't use too high value with this apodization. That's, let's say, one message from the example that we are showing now. Usually for protons, if you have like some normal concentrations, we use between 0 and 1 Hertz. It depends on the situation. But yeah, that's how we use it. Yeah, next thing that we can do here is this icon here. This is phasing. So this can be also accessed here from the menu. You can see, so we have apodization, then we have phasing somewhere, phase correction. So usually I use just the menu here at the top. So we can do automatic phasing. This software that we use today, I mean, or nowadays, it's really advanced. So usually if you do some automatic phasing, you will get really good phase. This means that your signal is like symmetrical. You don't have like problems. I don't know if you saw something like that, but let's say you open file and you get the picture like it's here. So this is usually means that phasing is off. So on one side you have like a bit of positive signal, on the other side of signal is a bit of negative. So if you have situation like this is usually a problem with phase. This is just to show you what is bad phase, because usually when you open the data, it will be very close to perfect phasing, let's say. So this is also the instructions that you have here in this blue window helps you or are instructions for how to use if you want to manually phase it. But so this is also an option. So you click on the position that you want to phase, and then you click and hold and then drag with your mouse. But I mean, you can play with this a bit. It's a bit harder to explain just with showing on the picture, or the other way that I said before. You can choose this automatic phasing here at the top of this menu, and then we can close this window so we can have a bit larger spectra here. The next option that we will check is baseline correction. Again, this is quite good in a way that it is, but we can check. We can see that there is a bit of some irregulars here at the
edges, yeah.
Yeah, at the edges of the spectrum, and then even if you check closely this baseline, so if we enlarge it a bit, we can see usually we would expect that baseline is at the same level on both sides of signal. So it's a bit off, this baseline. We can use the options here. So baseline correction. This will usually help to fit it to some polynomial function like is shown here, or you have other options. Again, we will not go through all of them. You can play a bit, check different options. Some are really harsh, so it will change spectra. I mean, change. If let's say if we take this Whittaker smoother, it will really go strict to your signal and to your baseline and try to improve to change it like it's really flat line as you see it now. So this is one option, or we can do. So if we use these are like these two I personally use the most. So with this Whittaker smoother or polynomial, usually polynomial because it's not so harsh. Here you can adjust what type of polynomial function it will be using, and this will try again to improve your baseline again. It depends how much editing you want. I mean, for this type of spectra where you have really good signal to noise, you can see that we have good signal to noise, and signals are well resolved. We actually don't need that much editing with baseline. And then let's say we go to the next one. So we will check the reference of spectra. So this is also quite important part. Again, we want to check what solvent do we have. So I don't know if we talked anything about this. Not yet, yeah.
Not yet, yeah. But yeah, this sample, the first example, this one is in D2O. And if you remember, I mentioned that for NMR, it is very important that we have the deuterated solvents, yeah. So this one is in D2O, and we added also a little bit of TMSPA for the reference. So Damian will show you where it is. But in the next example, the next one will be, I think, in deuterated chloroform. So we will see also the signal for that one. But yeah, in this case, since it's in D2O, you can also expect a little bit of H2O inside. So this signal of H2O, it's here around a little bit less than at 5 ppm. Yeah. So this is the signal from H2O, which is inside D2O, because it's not 100% pure D2O. Yeah. But yeah. In the case if it's in D2O, you cannot set up the reference on the solvent, but in the case, as we will see later, if it's in chloroform or DMSO, we can set up the reference on the solvent directly, but in this case, we will set it up to TMSPA, which is inside. So yeah, Damian, go ahead.
So TMSPA signal is at 0. So this one that we have here, it's quite good, but we will check it. So we can use this icon here. So the next one next to this baseline, so it's reference. Usually we can also use this shortcut. So this is L now. So if we check this reference and then go to the signal, you will see that while you go across this your spectrum, it will like stick to the peaks. So you go around this 0, and we already have it at 0. But in case if it's not, or is some other value, or you want to do it exactly and it's a bit off, you can type the new shift here in this window, or you can use this solvent table that you have also here. So if you have some solvent that you're not familiar with with its chemical shifts, you can just check in the table and then use the right one. So in this case, we are looking for this TMS signal, so it's at 0 and it's singlet. So all this information, it's already here, and we can do OK. So if we will do it in this way, it will also mark that this is TMS signal that we have like here. So I think this is, I'd say, this is few basic steps that we need to do, and now we are ready for some analysis. In this case, what we are interested in are integral values, multiplicity, and this is more or less it. Yeah. So again, we can.
And maybe Damian also coupling constant.
Yeah, multiplicity. Yeah,
multiplicity.
It's also with couplings. Yeah. So we will zoom in this region of spectrum. So let's say we are not that interested now in this water signal and TMS. So let's zoom in this region in between. So we have it like here. So we can see that in this region, we have 4 signals, and we can continue in this menu up there. So picking, integration. Maybe we can skip picking because it will also do it for us in the next step. So let's go straight to integration. So for integration, let's do it now manually, or we can use this option here, or again, we have shortcut I for integral. And what we have to do is just check one edge of our integral region, and then we click and drag it over the signal. So like this, let's say, and this will already, it will put some value at the bottom. And we do this also for the other 3 signals. And that's more or less it for now. So what we have here now is 4 values like 1, 1, 1, and 1.5. So usually Mestre now will set your first integral region to value 1, and then it will calculate all the others with respect to this first region. So obviously this is not the right, I mean, the ratio is the right one, but it's not the right normalization, because we have like 1.5. Obviously we don't have 1.5 proton in our compound. So what you want to do is just fix these values to integer values, yeah. So whole unit. And you can see, yeah, it's 1, 1, 1, and 1.5. So if you multiply by 2, it can make more sense. So what we can do is get to one of these signals that we want to edit, and then click with the right button on your mouse, and then click this edit integral. So, and then here you can type the value that we want, and let's say that we want to put this to 2, and it will recalculate all the others. So now it makes more sense. Yeah, we have like 2, 2 and something, 2, almost 3. So this is 2, 2, 2, and 3. So we are almost there. So what if you remember from the beginning of our exercise 1, we have like 10 protons. Yeah? And here we have 9.
Yeah, so our formula is C4H10O, yeah. And now in the NMR spectrum, we can see integrals, we can see signals which belongs to nine of them, like Damian mentioned. So there should be another one, but since we have this oxygen inside, we can also expect that this oxygen, the last proton will be part of OH group, and this OH group, since the solvent is D2O, this proton of OH group will exchange with deuterium from the solvent. So the signal would be either very broad, or we will not even see it. Maybe this one, which Damian marked it now, close to the water, maybe this one belongs to this OH group. Yeah. So Damian, maybe you can also, if you take a little bit, we can see also some smaller signals beside each signals. Yeah.
Mm-hmm.
And these signals belongs to, these are the satellites. Yeah.
Yeah.
You can see these are not the impurity of the sample, but these are the satellites which are due to the splitting, since in the sample you have also 1.1% of carbon-13, which is, and also you have attached the protons to this carbon-13, and these are so-called satellites, and you would always have it in NMR spectra. So maybe now we can just take a look a little bit of chemical shifts. So maybe we can go to this signal, which is integrated for almost free. So
yeah, just a second, excuse me. Sorry.
Okay.
I suggest we do multiplicity, because if we do multiplicity, we will automatically also get chemical shifts. We could do chemical shifts before, as I said. It's also picking. It's here. It's before integration, like in this way. But we can skip it and go directly to this next one. So this is multiplicity tool for measuring couplings. So we will do this J. So J is this coupling constant, and we will do this manually. Again, we go on the left side of the one signal, and below all these three peaks of the multiplet. So like this, so we get all these signals above our cursor. And so in this way, we will automatically get, as you can see here, notation for multiplicity. So this T or for triplet, and chemical shift. So it's just one step instead of doing it separately for picking. And in the same way, just typing J again and go over in this signals here on the right part of this proton spectra. Yeah. So this is the fastest way to do it. Yeah, I think. I mean, it's manually, and you get all this. So you get chemical shifts and multiplicity for the signals.
Okay, Damian, and maybe now we can zoom this one at which is a little bit below 1 ppm, yeah. Just to see how the signals look like. Okay, we can see it here. We called it a triplet since it consists of 3 signals of different intensities, and we know that from chemical shifts, first it is important the chemical shift, then this multiplicity, and also for how much it integrates. So based on that, and we can say that this signal belongs to CH3 group, yeah. So maybe I can share it. I will just share it and maybe try to. I will see if this will work. Just Damian, stop share it.
I stop.
Just stop sharing, and I will share. I will see if this will work. Yeah. This is whiteboard. Just to see. Okay. But otherwise, you can also. So we said that we have the molecule. Do you see this? What
yeah.
Okay. C4. Our molecule is C4 H10O. So we need to figure it out what it is. Yeah. So we know that we have four carbon atoms. And we now also figure it out that we have CH3 group, yeah? So this signal, which we saw it at a little bit below 1 ppm, I think at approximately 0.8 and something, yeah? And it integrates for free. So we see, I think, this kind of signals. It was a triplet, yeah? Triplet. And this means this triplet tells you how many protons is on neighboring carbon atom. So in the case of triplet, on the neighboring carbon atoms, there are 2 protons. So it's always -1. So if there is a free signals, it's -1. So there are 2 protons. So on the neighboring carbon atoms, there should be 2 protons. Yeah. And also, this one will have or maybe we can go back to the Nmr spectrum and see how the other signals will look like. But yeah, for sure, this signal, which is a triplet, this tells you how many protons is on neighboring carbon atoms. So for this one the signal will look more like some multiplet because these protons are coupled with protons here as well as protons on this carbon. Yeah. So at the end I will just wrote OH. So if we have here, Damian. Here I will write another 2 and here another 2. So okay, for this one, these protons are coupled to these protons here as well as to these protons here. So the signal will be something like, it should be, due to this one, it should be a quartet of triplet. And this one should be triplet of triplet, but in the reality, we will see how this signal will look like. And this proton here will be due to these protons here, again a triplet, because the coupling constant to this OH group, if it is, it's quite small, yeah? So now we can go back and see if we have another triplet in the spectrum, and then if we have something like a quartet of triplet, triplet of triplet, some multiplets for those protons here, yeah? But also from chemical shifts, this CH3, it's, let's say, around 1 ppm, and these signals are around 2 ppms. And closer there to some heteroatom, like this oxygen, the chemical shift is higher. So this one we expect from those three, this proton should be at the highest chemical shifts due to this oxygen here, yeah? So I will stop sharing and you can.
Let's do a few minute breaks.
Okay, then since Damian have some problems with microphone, I would suggest 10 minutes of break and then we can continue if you agree.
Okay.
Okay, and yeah, let's be back in 15:45, yeah. So yeah, if you remember before the break, we just figure it out that this CH3 group, which is for the signals for protons, so these CH3 groups were a little bit below 1 ppm, and the signal was like a triplet. So this, just to remind you that since it is a triplet, it means that on the next carbon, on the neighboring carbon, there are 2 protons. So it's always the multiplicity minus 1. So for the next one, if it's something like that, since we know the empirical formula, we should expect something like that. As you remember at the beginning, I mentioned this index of hydrogen deficiency, and we know that it's no double bond, it's no ring, and so on. It should be something like that, this kind of linear molecule. So for this CH2 group, for these protons of this CH2 group, we should expect some multiplet signal, which would be integrated for 2. So it's due to these 3, it should be something like quartet, and due to these 2, quartet of triplet. And in this case, due to this 2 and due to this 2 on the other side, this one should be triplet of triplet, or we will see how it will look like in the Nmr spectrum. And for this last CH2 group, we would expect again something like a triplet due to these protons here. We would not expect, or just small couplings to this OH group. So yeah, I will stop sharing. And now we can check, Damian will check, we'll start to share his Mestre Nova, and we will see how this looks like in NMR. So yeah, okay, yeah, this triplet which belongs to this CH3 group, and now we will go further. So we can zoom all this, yeah. And we can see that now we have 3 signals, but this one, not signals, but there are more signals. So we have 3 parts, or how you would say this, sklopi signalov. 3 sets of signals. Yeah, one is here, and they're all integrated for 2, so they all belongs to CH3 groups. But now we just need to figure it out to which ones. So maybe if we zoom, we said that this is the last one before OH group. If you remember, it should also look like a triplet. And as you can see, this one at a little bit at around 3.6 ppm. Look, it is also a triplet. So this one belongs to this CH2 group, which is next to OH group. Yeah, and if you remember, I said that if there are some heteroatoms inside the molecule, like oxygen, nitrogen, the groups next to these heteroatoms will have higher chemical shifts. So it means that a CH2 group, which is closer to OH group, for instance, it will have higher chemical shift. So this is also true in our case. So this group, which is here with a represents as a triplet, will have the highest chemical shift in our molecule, and this is also the case here. Yeah. So yeah, maybe we can zoom it the other 2. So now we should zoom the other 2. So if you remember, now we have 2 and 2 CH2 groups, and you can see that these sets of signals, they both integrates for 2. So they belong to 2 protons each. So it is at 3.33, and the other one it's at 1.51 ppms. So now we just need to figure it out which one is which. And yeah, Damian, you can say something about that, or?
Yeah, what we can maybe check here before we do anything else is we can lower the optimization. Maybe this is a good idea because as not me, as Primož explained to you, you expect like triplet of triplet and quartet of triplet, but what Mr. Noah proposed here is like this P, so pentet, and H, heptet. I mean, they can be, but sometimes if you use too high value of filter, what we showed before, this really fine resolution can be lost. So let's see what we can see without filters, and you can see that actually you have some really fine multiplets. So this P that is stated here is probably not the right classification of multiplet. That's why, because we expect more like quartet of triplet and triplet of triplet. So sometimes this automatic processing is not the best way if you want to understand the multiplicity correctly. But probably, yeah, to really know which one, we will have to use maybe some carbon and HSQC. Or what did you mean, Primož? Or you have some other idea?
Yeah, first we can already say something from chemical shifts. If you remember, maybe I will just stop sharing, Damian. Yeah? I will just share this whiteboard again. And already from chemical shifts, yeah, this one, due to this OH group, we would expect this one at the lowest chemical shift, which is true, which is at a little bit below 1. So this one would be expected as a little bit higher chemical shift, and this one even more higher, and this one at the highest chemical shifts. So based on that, we can also say which one is which one. So this one would be next to, also in the proton NMR, it would be next to this CH3 group, and this one will be closer. This one will have the lowest, then this one, this one, and this one will have the highest chemical shift. So based on that, we can say that which signals belong to which one. And like Damian said, we will also check the carbon atoms and HSQC. So we will also correlate carbons to the protons. So we will say, these carbons here correlates to this these protons here correlates to this carbon here, and so on. So we will do this with HSQC spectrum. But yeah, maybe first we can just check how it looks. Okay, maybe we can go back to the proton and then to carbon and then to HSQC. Yeah? So I stop sharing. Damian, you will?
Yeah, sure. I just need to click a few times.
So yeah, based on that, what I said, most likely this at 1.3 and something, these signals belong to this CH2 group, which is next to this CH3, the first one, yeah? And this at 1.5, they are the next one. So for the last one, which is a triplet at 3.6, if you remember, maybe just zoom it out.
I'm trying.
Yeah, this one this one, okay, this one at 3.6 ppm. This one is this belongs to CH2 group, which is next to oxygen atom. And now maybe we can go and check how the carbon spectrum looks like. And we know that we have in the molecule 4 carbon atoms, so we would expect.
Yeah, one more thing maybe before we go on. What we didn't mention till now is this multiplicity, so value of coupling constants. So we have multiplicity like this T for triplet. So it's very easy in this Maestro program. If you double click it here on this one, we will get another window. And here you have also the value of coupling constant. So this 6.6 Hertz, this is the splitting between two peaks. I mean, on both sides. So with this, we can also evaluate which part of spectra are really coupled together. Sometimes, if it's not too overlapped, or like this fine couplings that we have here. But yeah, for this one that is well resolved, we can see really good. So 6.6 Hertz, and these are typical values for 3-bond correlations. I mean 3-bond couplings, like we have it here. Yeah, if we click on this button here, so we have like next one. So next multiplet would be this one. But here, as we said before, this pentet that was evaluated like automatically, it's not the best fit for this multiplet. So these values are like approximate. So we would have to do it manually to do the proper evaluation. And also here we have like more the small splittings. So these are not the best one. But yeah, the last one here, this triplet, is again quite good. So this is 7.4. And yeah, one option to see which are neighbors would be if we find this 7.4 and 6.6 Hertz. If we found these couplings in this multiplet here, we would know which are neighbors in this compound also. Yeah, but we will not go in too much details now. Probably we'll just go on to the carbons. So the carbon here, you can see we have singlets. So this is proton decoupled spectra, so no couplings. In this way, it's much easier, and it's usually recorded with decoupling. So we have like singlets for all the signals. What we can do is we can manually pick out this picks, or we can do like this. So pick by pick is 1 by 1, or we can do manual threshold. This means that everything above some range, like we show it here, it should be assigned as picks. So in this way, we can get really fast these chemical shifts that we have here. Then the third spectra that we have here, it's very similar to carbon. This is depth 135. Again, we can use probably the same or not, because there are some negatives, or we can do so pick by pick. So now I choose this option here from the menu. So pick by pick means we can go over signals and it will stick to them. So if we click when it's on the signal, you will get also chemical shifts. These chemical shifts are more or less the same as here on this example. So in general, it needs to have the same values. So what is benefit of this depth spectrum? In carbon spectrum, we have all positive signals that we see here with depth 135. We can, with this depth spectra, we can play with parameters, but in general, this 135, it means that some of CH groups will be positive and the others will be negative. And 135, it means that CH3 and CH groups, so with odd numbers of protons, it will be positive, and then even numbers, CH2, will be negative, like we see it here. So yeah, as we said before, Primož already draw a structure or a bit of structure, and we have like CH3 and then 3 CH2 groups. And we also can confirm this with this depth 135. So we have this positive signal of methyl group, and then we have 3 methylene groups with different values. Again, similar to proton, the one that is most downfilled, it's probably next to oxygen, and then the other 2 are in between. I mean, this molecule is quite simple, so maybe it's not really much to tell more about it, or?
No, maybe now we can just go to the HSQC, that you will see how we can correlate which protons are connected to which carbons, yeah.
Mm-hmm.
Just to see the idea of this type of spectra.
Yeah, again, here we will zoom in maybe this region where it's the most of all, or even all of our signals.
But
And
maybe just one, sorry, Damian, but maybe just to tell you that this Mestra Nova works like that. If you already have before opened, this proton spectrum as well as carbon spectrum, when you open 2D spectrum, it will give you these protons or carbons at both sides of these 2Ds.
Yeah. So the actual data of 2D is the one here. Yeah. So this is this plane, and then what we have above is actual, as Primož said, the actual proton spectra, and on the, so I'll just move it back, and on this left side is the actual carbon spectra. So it's combination of all this data that we have. What we can see here is that our reference in 2D is a bit off. So I wanted to check if there is some TMS. I mean, we have TMS inside. You can see it here. Yeah, but this signal is quite low, probably for this 2D. So if we enlarge the vertical scale, which is like up, I mean, towards us in this 2D case, maybe it's this one that's really low here. But if we are not sure, what we can do is we can check the signal here. So maybe we roll back to Proton and check what is the value of this metal group. So we can see it here. It's 0.89. So this value here. So we can go back to HSQC and let's zoom in this part. So this one is actually at 0.89, and what we will do is just click again with this ruler. So reference, you have it here. So you click on reference, and let's choose this middle signal here, the middle one. Yeah, and similar to 1D, we can also set up a reference here. So as I said, we checked in Proton and that this one should be at 0.89. We could also change the other dimension. So F2 here stands for direct dimension, and this is Proton dimension, because this is direct dimension that we are measuring. The F1 stands for indirect, and this is carbon. So if we click here to carbon, we could even edit this one, but I think that carbon is quite well aligned. So we will just change this proton chemical shift. So on the actual signal, not TMS, because we don't see it, and we use 0.89 and click OK. And this will then align your 2D signals with your 1D signal. And if we check, we can see that carbon signals are aligned better, so we don't need to modify it at this point. So it's quite good alignment in carbon dimension. And yeah, what Primož showed before, these protons are now, I mean, the signals that we observe in HSQC are direct pairs of proton and carbons that are connected through one bond. So this metal group, so we know that this metal carbon and this metal proton are connected. Of course, it's only one of them. And then we have this CH2, the next CH2, and so on. So if we check this part, we will see it here, all these signals.
Do you have any questions about the first exercise, or we can slowly move to the next one? Okay, if there is no further questions, yeah. So maybe we can continue. Diamond, just stop sharing. I will just show the molecule.
Mm-hmm.
So I will share the screen just a little bit. Oh. Okay, this one, share. Do you see it now?
Yeah.
Okay, so maybe I will just make it smaller. So now we will continue with assignment of this molecule. This is Ibuprofen. I think everybody heard about Ibuprofen. So it's a drug molecule which is used against pain, like in different drugs. I don't know, paracetamol or no, paracetamol, it's another one. But yeah, if you have some pain, you can use this drug. So using this one is a little bit more complicated than the one which we worked on now. And we will try to assign all these protons, which are marked here with, you can see this number 1, 2, 3, 4, 5, and so on. and we will try to assign all these signals. For instance, for this 4, we will try to assign the chemical shift of this carbon as well as of these protons. And this we will do for everything and for all these atoms here. And this means that at the end, we will say, okay, this molecule is present in the sample or this molecule is not present in the sample. This is verification. So yeah, I will stop sharing, but in the when we will assign some signals, I will again share it, and we can beside the signals, we will write the chemical shifts. And when we will do everything, so when we will use all the spectra, everything should fit if the molecule is the right one in the sample. So yeah, I will stop sharing, and Damian, you will start to share now the Nmr Nova. So here we have, you will see here, we have also, now we can all just close all this, what we have it now. Yeah, so we don't have any spectra, so we can open, this is the second. This is this Ibuprofen in Chloroform, CDCl3. These were spectra which we recorded last month, so just for these exercises. And you can see there is so many of different spectra. So we will start with proton, and maybe just to remind you, yeah, maybe we can open the first one and then we will go to the second one, yeah, and you will see the difference. So maybe just open this first one, which is, yeah, and this can be opened with, yeah, okay, you can open it with fit if it, so yeah, okay. And maybe you can just enlarge a little bit if you go up.
Like this.
And this is full spectrum, or?
Yeah. This is full, yeah.
Okay. And then, okay. Because I also recorded with larger sweep, and in larger sweep you can see a one bump, maybe which belongs to some OH group, or just for comparison maybe. At this point, I just wanted to say that sometimes you should have sweep which is large enough. So if it's too small, you maybe just erase some signals from the spectrum. But in the case of proton, if you don't know where the signals are, you can go, let's say, from -2 up to 20 ppms, and I think this is enough. And then when you know it, you can make it make it smaller, the sweep. So maybe just you see the signal here. So you can see this broad signal around 12 ppm, between 11 and 12 ppm. So with the smaller sweep, when we acquired spectrum with smaller sweep, we didn't see this signal, yeah. So that's why I'm saying that first it's good to go to measure NMR spectrum with larger, and then you know where your signals are, and then if your signals are not at these high chemical shifts, you can just make it smaller window for measuring, yeah. So yeah, this is then proton. Here you can see that it's already more complicated. So maybe this is in chloroform. So also in this chloroform, it's usually present TMS. So we can also see signal at 0 ppm. This is for the reference, and it's usually inside. When you are using chloroform, it's already inside the solvent. So you have it. You can set the reference on this signal or either on the signal of chloroform. And if we take a look of this solvent table here, we can see, if we take a look, if we find a chloroform, it's this one, and it's the solvent by itself should have a signal at 7.26, and it should be a singlet. Multiplicity, you can see it's a singlet, and we can also find this signal in the NMR spectrum. And this is TMS. Yeah, we can set it to TMS.
Yeah, now we are on TMS. That's why we need, I mean, if you want to change, you have to set to TMS because we are at 0. If we go then to that region around 726, we can see around here. Yeah, it's probably this one.
Yeah, it's this one. This one is the peak of Chloroform, which is a singlet.
Yeah, so this is 725, very close.
Yeah.
But it will never be the same. I mean, like 726 because it's a bit of discrepancy. But yeah, it's there. So yeah, this is Chloroform.
So maybe we can just open the other spectra or just go to integrate this one. Yeah.
We can work on this one.
Yeah,
and then open
go
the
further.
others.
Yeah. Okay.
So we will do very similar to before. We won't play now with this apodization and phasing probably because it's okay. What we can do, we can maybe do some baseline correction. Yeah, but this broad signal here, it will make some problems. So we don't want to be, and that one would be like discarded because we know it's the signal. So it's very broad, but it's there. So let's maybe let's focus on this region here for now. So I will start, I mean, it doesn't matter where we start, but let's say we'll go with this one here because these are like well resolved, nothing around. So it should be quite easy to integrate. Usually I try to integrate like from between the satellites that we explained before. So these are these carbon satellites, and if you integrate the region between these two signals, you will get really close to like quantitatively correct assessment for this integral values. And we have also two signals here. So maybe we go from really close to chloroform, and then also this one here. Okay.
And if you remember from the beginning, from this short presentation, or already from chemical shifts, we can say something. So this signal, for instance, between 7 and 7.5 or a little bit less, they belong to these aromatic protons, which are in this Ibuprofen. Yeah. So yeah. And this signal, for instance, which is below 1 ppm, should belong to this CH3 group. So if you see in the spectrum for some unknown compound, such signals which are between 7 and 8 ppm, you can conclude that these are most likely to belong to aromatic protons, and signals around 1 ppm or up to 2 ppms most likely correspond to some CH3 groups. Yeah. Okay.
So how are we doing? It's too fast or it's fine? Probably
Yes,
it's okay. There are no complaints. Okay, nice. Yeah, so let's continue. So we integrated all of our signals that we see here. Let's just continue with multiplicity. So I will zoom in this region of this aromatic signals. So we do it like with J, or you can use the shortcut with the icons.
Damian, just one question. How much is this exponential function here?
Yeah, we can check. So it's 0.3. Yeah, this is about right. I mean, again, we don't have problems with with sensitivity, so we have really good concentration. I mean, nice concentration of sample, so we don't need to play around. think it's good enough. Yeah, and then we switch to this region here. And again, with J, we can do quickly this evaluation of multiplets. Yeah, probably observed we have like two integrals here now. This is some automatic property of this Nmr, but we can, if you want, we can switch it off. It's quite easy. If we so make a right click with the mouse and go to properties, here we can set up all these like fonts, colors, and so on. And so this is like multiplicity, all this multiplets part, and then we have multiplet labels. It's okay. We have this sub option, let's say, in this menu. So integrals are once more. So these integrals here are the one that we set, and then when you do multiplets, it can do one separate type of integration. I mean, it's the same, very similar integration, but it's twice in the spectrum. So we can just turn this off. So what we can do here under multiplets, we choose no labels for integrals and no range for integrals. This one here, if you do apply, it's a bit less messier. So we have only these integrals that we did manually. I think we are more or less ready. I mean, now we have these multiplets. You can see they're quite nice with this quartet here. Then we have doublet, this double pentet. We'll see how is this one. Then another doublet, and so on. So if you want, you can click and check the values similar to before. So we have this 7.2, 7.2. So maybe these two are connected. I mean, the part of the same coupled system because of the same values. So here are two values like 13.6, 6.8. Then we have 7.2. So it's a lot of the 7.2. So maybe it's not that straightforward, but maybe they are part of the same system, and 6.6. So this is just quickly to see through these couplings. Yeah, maybe before we go to assignment, we open the other spectra also. So proton is ready. Let's open carbon next.
Yeah, carbon and carbon depth, we have it.
Yeah.
And the
carbon,
first one is carbon, yeah.
We can do FID. So this is carbon here. Yeah, we can see it's a bit, at least mine is like leaning a bit. So we'll do baseline correction. Okay, so it's straightened. And then we can do just picking and.
Or maybe just, Damian, before we can just set up the reference if it's not, just to check on the solvent.
Yeah, but we can do later.
Yeah, okay.
Maybe it's just to see values. I mean, it doesn't matter which is first, but so we can do like this quick manually. Yeah, so we have probably, this is TMS or not? Probably yes.
Yeah. This
so we
one
can
is...
set it up to this TMS signal here. It's quite weak, but it's there. And then we have also solvent signal for chloroform at around 77. If we are not sure where it is, we could do even like go to this TMS. So again, I hope it's not too fast. I typed L just for this reference, and then we go to this one. So this can be put to 0, or if you go to solvents, you can check TMS. So TMS is quite nice because it's always at 0, no matter if it's carbon or proton. So we can do this, okay. Or yeah, what I want to show, but then now it's too fast. If you're not sure about chloroform, you can check it in this table again. So chloroform, it's around 77.16, and it's like triplet. with this multiplicity, with this coupling constant. So this is also option, and we can check it. So at 7.7, we can check it here. So yeah, we see it. So the middle one is at 7.16, but this is quite good. I mean, it doesn't really matter. Just maybe you need to write to which signal you referenced if you make it for some publication or some report. So it's consistent. We have question or something. Echo. You'll mute it now, or?
Now I will unmute myself, so I hope it will be.
I'm sorry, I have a
So
question.
I hope now it's fine or back to normal with audio.
Sorry, some questions?
Yes,
No,
I
just
have a
the
question.
audio issue.
My name is Vladislav. Can I ask you?
It's okay.
You can ask. Yeah, just ask.
So basically, you determine this G coupling constant as integrated peaks.
Yeah, so we have chemical shifts for carbon.
So
it's quite fast. So we did a lot of automatic, but usually this spectra, I mean, for this compound, it's quite nice. So we don't have like impurities and so on. So it's really fast process. Let's go on with the next one. Which one, for chloroform?
No, sorry, you asked for coupling constant for chloroform, or?
No, I mean, how you determine them from the peaks from integrating each peak in multiplets, as I understood. But how do you use these constants afterwards to construct the formula of, for example, ibuprofen? I don't precisely understand how it helps in. I understood the technique about chemical shifts, but I don't precisely understand how do you use this G coupling constant.
Okay.
But
yeah, we'll go back to protons because they're here, these coupling constants. Yeah. So if maybe in this case, it's not like the best example because we have quite some similar coupling constant. I mean, it's still good, but let's try to explain. So if we check this quartet here, we can see the value. This is 7.2. So if we would have, let's say, if we would have just two signals in proton that would have this 7.2 hertz coupling, we would assume quite good, I think, or quite accurately, that these two signals are coupled between themselves, because coupling constant is like reciprocate, so it's the same from one to the other signal. And if it's observed for two signals, the same value, we could say that they are like coupled between themselves. So this is one option. That's why I said, okay, if this is 7.2 and then the next one here is 7.2, that's why I said these two signals are probably coupled. But it's not necessarily true, because we could have the third one that is also 7.2, and then it's a bit more, I mean, we need to do a bit more work because you could have very similar couplings. Usually these 3-bond couplings that are for like free, that have like quite free rotation around their bonds, it's the coupling constant is around 7, and then you can be 6.7, 7.2, something. So if you have like free rotation, it's very similar for all these examples. If you have some different let's say restricted rotation, you could have like coupling constants less or more than 7 Hertz. 7 is like an average. I hope I explained a bit, or if it's
yes, yes.
Yeah.
Thank you very much.
Okay.
Yeah, maybe I can also show you again this table which I showed in presentation, or where you can, from the size of the coupling constant, you can also figure it out, this trans or cis conformation. Yeah. One thing is this, which Damian said, which are coupled together, so they should have the same number. But the other thing is also the size of the coupling constant. It tells you a lot, the size, how the, let's say, but I will share it. Damian, you can stop sharing. I will just share it for just to find. Okay, do you see it? Yeah. So here I just wanted to say, for this coupling constant, for the size, yeah. So if the protons are like in here in this trans conformation, so one is on one side and the other is on the other side, and for this one you will see a doublet. So this one, the coupling constant is between 12 and 18 Hertz. And due to this one here, and if they're on the same side, this one will be also a doublet due to this proton here, but the coupling constant will be lower, between 7 and 12 Hertz. But it's like that. This one is coupled to this one, and this one is coupled to this one. So they should have both the same splitting, and also in this case, yeah. So this I just wanted to say, yes. So
Thank you. Thank you.
Welcome.
One example also we can check here. I mean, this is in a way quite obvious because it's this aromatic part is like coupled, of course, between themselves, but these couplings are usually a bit higher than like this methylene or methyl groups. So this doublet here, if you click it here, you can see 8.1. So this is higher value. And of course, this means it's not coupled to 7.2 because it's quite different. And yeah, the other one here is it's a bit, you can see the automatic processing that was done. I mean, from this with the software. So this doublet is okay, quite good determined. This one here, it took like more of this signals, and it says it's multiplet because it cannot determine what is the value. So maybe just one thing why you have this type. So in this aromatic group, we don't have just 3-bond couplings that are the most expected, but we have also some long-range couplings via 4 bonds, and that's why we see this small, let's say, irregularities in these signals. But the main coupling is this doublet between the neighbor two protons, like proton 8 and 9. Do they have this picture or no?
Yeah, they have this picture. Yeah.
Yeah, so this is a bit different value for coupling constant for the aromatic part of molecule.
But Damian, for this aromatic part of the molecule, I can show it here, this ortho-meta para, yeah?
You can show, yeah, if you have it ready.
I have it, just...
Because, yeah, this is the example that we are talking now.
Yeah, I will show it. Again, I will share. This is in presentation, which you also have it. So you can see here at the bottom, if this proton here, you can see, and it can be coupled to this one here, here, and here. So they are ortho, meta, para positions. So like Damian mentioned, this one to the next one, which is ortho position from this one, it's the strongest one. It's between 6 and 9 Hertz. I think you said 8, yeah? And then this one can also be coupled with this proton here, This is ortho, this is para position, ortho, meta position. And this one is a little bit, it's smaller, it's 1 to 3 Hertz. And it can also be coupled to this one on para position. So, but this one is really small, between 0 and 1 Hertz. But due to that, you don't see only a doublet, but you see these signals like Damian showed you right now. Yeah. I will stop sharing.
Yeah, maybe we move on with more spectra. So which one do you suggest, Primož?
Yeah, just open depth, yeah, and then yeah, depth.
Yeah, I had to move it. Okay, so this is depth for this compound. So maybe not that interesting. Or yes, yeah, it's only one. It seems only one negative signal. This is this one here, and the others are positive. We can do like this fast picking, and manually for this one. So we have these values, and we can also check the reference. So again, this should be TMS because we don't expect others at around 0. So this is at 0, and now we have these values for chemical shifts. Yeah, so this can help us determine some of the signals here. So what you can also see, if you compare, now we have a bit more carbons than before in the first example. So what you can see, some signals are missing in depth. So for this type of depth 135, we don't see carbons that have no protons attached. So like some carboxyl groups or some others, or these quaternary carbons that are, let's say, on this aromatic ring. And these are mostly all of them in this example. So you can see that these signals here, so above 130 ppm, we don't observe in depth. Let's add some more.
Yeah, maybe HSQC and HMBCs.
Yeah, these are quite regular to use.
See, just open it with, yeah, this P data, and then this one, yeah, click one, and then this 2RR. Like that, the Mestre Nova will open correctly this HSQC spectra. Otherwise, it's not correctly opened. Because these spectra were measured on Bruker, and with Bruker topspin program, it's open. You can nicely open it, but with Mestre Nova, you should do like that.
So you see the full path. So SHQC, P data 1, 2RR. That's okay. And we can open one more.
No, maybe we can open still HMBC and
Yeah,
maybe
yeah,
Toxy with lower mixing time, with the lowest one, yeah.
Okay. So HMBC will do the same, P data 1 and then 2RR. And we'll do one more. So Toxy 20.
Yeah, Toxy 20, it's the same as Cosy. So you just see the direct connections through free bonds. Let's say proton is correlated to the next proton through free bonds. So yeah. But later on, if we will have time, we can also check Toxy 80, and you will see that In that case of Toxi 80, this means milliseconds of mixing time. The magnetization will go further, so the protons will not be correlated only to the neighboring protons, but also to the other protons of the molecule if they are in the same spin system. And this we just need to set up the reference, but this is the easiest way to do it on TMS.
Here I enlarged this vertical scale for 2D, and then you can see this a bit weak signal here. This is around 0, and this is probably our TMS because it's the only one around there. See, so we will zoom to this region. So this one, it's a bit off, but we will do it with L. We can do it with L. Click on in the middle and then do 0 in one dimension and also in the other, so for proton and carbon, and just click OK. So it will be corrected to this value here. And then we can lower the scale, because if we increase TMS, it's really weak signal in this spectrum, and then it will also, we can see some like small signals that are maybe some impurities or imperfections, but it's quite okay like this for HSQC. Should we stop here now, or do you want to, to check something on HSQC? Maybe one thing that we can mention here is, so these modern HSQCs, or modern, that are measured nowadays, you will see that there are some, there are usually two colors of signals. So you see that most of these signals here are red, which are positive. And then we have this one blue here. So I'll just maybe zoom in this region. So you can see here we have these red signals, and then this one is blue. So this is similar information that we get from depth spectrum. So this means that this group here is probably CH2, so it's negative, and the others are then CH or CH3. And this is also what we expect from the molecule of ibuprofen. So this CH2 can be quite easily identified.
Yeah, there is only one CH2,
Yeah.
in the molecule, yeah.
Mm.
Hmbc, you also set up the reference?
We will check. So Hmbc is this one here. Let's check this part. We will enlarge it a bit. I think it's this one. It's also a bit off. So put it to 0 and 0.
Maybe just to say, yeah, maybe just going back to see these signals, yeah, because they were free,
Sorry?
Or not? No, because in Hmbc, usually you should not see correlations to through one bond, yeah, but this is, if you can say something about, you can still see correlations through one bond, but it's like that you see free signals, yeah? You know what, remaining correlation through one bond.
Yeah.
But, okay, maybe we can see this later if you will see it, okay. Maybe we can just go to assign our ibuprofen, yeah?
Yeah, so let's go maybe now to assignment a bit. So some ideas where to start. I mean, we talked about about some signals already, but do you want to join us in assignment? Where to start? Some suggestions. What do we know about signals already? So the idea, or let's say the goal is that we know chemical shifts for all carbons, for all protons, and then for protons also multiplicity and coupling constants is if possible.
But Damian, maybe if we take a look a little bit proton spectrum again, we can no, the second one you did it more, yeah. And if we look, and we can see if we just zoom it, this region, let's say between 0 and 2 ppms, or maybe hold this region, yeah, doesn't matter. So we can see that you can see that we have below 0, we have one signal at 0.89, and you can see that as we know it from before, that this signal most likely, not most likely, but it belongs to CH3 groups. And you can also see from the integral, can you tell us from the integral value how many CH3 groups should be inside this signal? Can you tell us? You can see that the integral value is how much? It's 6, yeah? So it's 6, and this means that there should be 2 CH3 groups which are in identical environments since they have the same chemical shifts. And if we take a look at the molecule, maybe I will just, or you can present it, or I can, the molecule, you can just stop sharing and I will share the molecule. So yeah, we can now see this, our ibuprofen. So we said that this signal, which is at 0.89, and it integrates for 6, which means that there are 2 CH3 groups which are in identical environment. So if you take a look at this molecule, you can immediately see that these 2 CH3 groups are most likely this one marked with number 13 and this one marked with 14. So we can maybe start it from here, yeah? So, okay, I will stop sharing. Maybe then we can continue from these CH3 groups, yeah, using maybe or Toxi this with mixing 20, or we can also first assign, maybe we can assign also their carbon atoms, yeah?
Yeah, it's you can do it either way. Yeah, it's more paths to follow. As Primož said, we can do it Toxi, we can go to HSQC. It depends what is your preferred way. So let's say we can check in HSQC and check which carbon is for these 2 methyl groups. Yeah, and if you go here to around, so this below 1 or.
At this point, I would just like to say something. I hope that everybody has this ibuprofen. I have it on list beside me like that one. So you can take it and just write it down at each protons and carbons, their chemical shifts. And this will be much easier for us to follow the to get the final assignment. I will just do it here by my, and you can also do it by yourselves, just to write the chemical shifts for and for these protons, these CH3 groups, protons marked 13 and 14. I will just write down that the chemical shift of the proton is 0.89, And now we will also get their carbons, and then we will just go further. Yeah. So usually we do like that, that you take a molecule and then you write down the chemical shifts, and then you go through the whole molecule. Yeah.
Yeah, so for this one at 0.89, if we check correlation in HSQC, we can see that carbon is at around 22. And now maybe the best way, or to get the accurate chemical shift, we check in carbon spectrum, and we can see here that this 22.39 in my example is the one that's this value. What is also maybe additional confirmation, the intensity of the signal is higher with respect to other around here. So that means, because it's not like exactly proportional, like twice higher, but you can see it is higher intensity. That means it has to be, in this case, more than one carbon if we compare to the others around here. So this is additional proof that we have it's probably right in this case.
Yeah, but it's not like in Proton that you can integrate directly and see how many of let's say carbons you have it.
Yeah, I mean, it can be close, but yeah, it's not that accurate.
Yeah. So yeah, now we wrote if we take a look this ibuprofen structure. So CH3 group marked with number 13 and the other one marked with number 14. The proton is at 0.89 and the carbon is at 22.39 ppms. So this we marked it down, and now we can just go further further in assignment. So yeah.
Yeah. So now to move on, we can do it again multiple ways. So we can go with Cosy and follow proton-proton correlations, or we can go with Hmbc and follow proton-carbon correlations. So maybe let's go to Cosy. Maybe we didn't talk much about Cosy today, so let's check it here. So what we want to find now is what is the neighbor of this methyl group. So we are looking for this CH. This is 3 bonds away. So in Cosy, this is Cosy with mixing time of 20 milliseconds. This will give you the similar result as Cosy spectra. So it's just neighbors which are like 3 bonds away mostly. So the closest one. So if we maybe I didn't know. I don't know if you checked the reference.
No, the reference should be checked.
We'll do it quickly now. So I zoomed in this signal around 0 for TMS, and we'll put it to 0 in both dimensions. So here in Cosy we have proton-proton. So it's 0 again for both dimensions. And then let's check this region here.
Yeah, now we are looking for this CH, this proton of CH group marked with number 12, yeah, in the figure of ibuprofen, just to know where we are, yeah.
Yeah, so if we check this methyl group at 0.89, what we will see now, it's maybe interesting. So actually we can see 2 correlation signals. So yeah, maybe we didn't talk about Cosy much. So we have like this diagonal. If we check, imagine this line. So we have like this diagonal that is just the same as proton spectra. And then we have this out of diagonal peaks that are actually correlations here in this example. So if we go with cursor over one of these signals, let's say this methyl group at 0.89, all that are off this diagonal in both directions, so we can check it here or in this horizontal line. you can see that this chemical shift, we have actually two signals. Yeah, you see this one here, and then we have one more here. So why this happened? As I said, Cosy, it's not. I mean, it's very similar to Cosy, but it depends what are the couplings between this neighboring protons, and sometimes with a bit longer mixing time, we can see also the neighbors that are far away. So in this case, if we wanted to see just one correlation, we would need to do even shorter mixing time. Yeah. So in this case, 20 milliseconds will give us CH proton and CH2 proton. Yeah. So these are protons 11 and 12 from the figure of the molecule. But if we combine a bit of our knowledge of proton, so if we know this 183 and 245 ppm, we can check in the proton. We will probably know which one is the one that we are looking for. So the signals that are now in question are this one here, so 2.44 and 1.84. And if we compare the integral values, we can see that this is like 1 and this is 2. And if we again compare to HSQC or some other, we would find out that this one, yeah, is CH, because it's for 1, and we could confirm also in other correlations. So and this 2.44, it should also be in agreement with let's say HSQC, because we said before that this CH2 is the only one that is like that has even number of protons, and this is at 2.44. So actually we got both these two groups, so CH and CH2 on this part of molecule. So we can go and write down the values. So we have 1.84 for this proton at position 12, and then we have 2.44 for the one at position 11.
And now we can check their carbon atoms. Yeah, we can go to HSQC to see the chemical shift of the carbons.
You can do carbons. If you want, I mean, usually you can do also multiplicity. So this 2.44, it's clearly doublet, so it's really nice. Yeah, the other one is a bit trickier. The one we see here, so this 18.4, it's probably doublet is correct because it's as we said before, it's reciprocated with C11, so this CH2 group, so it is doublet, but then it's probably not pentet. In sense of theoretical expectations, it's like 2 quartets, yeah, because we have because it's coupled to both of these metal groups. So the correct assignment or the correct assessment of this multiplet would be doublet, quartet, quartet. Or maybe if it's the same, it's doublet, quartet, Decu, yeah, because it's the same probably CH2. As CH3, it's the same couplings to both. If you are not sure, sometimes you can just put M like multiplet, and yeah, it's maybe easier to put it like this. I don't think it's this DP doublet of pentet. So yeah, but let's don't stop too much here. So let's see the carbons that are at these two positions. So let's go maybe to HSQC, as we said before. So we have this one around 30 ppms is the CH, and then we have here are two very close. So one way it's to differentiate them here, or the best way would be now this depth, because we have it, yeah, in this region here. You can see positive and negative signal. So CH2 is negative. So the one that is a bit more downfield, so that's 45 and something, is the one that we are looking for. So we can go, usually it's determined from carbon. So let's go to carbon, but probably it's the same value. Yeah, it's the same. But yeah, just to make sure. So this one 45.04 is CH2 at position 11. And then we have the one at 30. So 30.17 is CH. This is position 12.
Yeah, so now we assigned all these signals of this CH3 number 12, 13, 14, 11. So now we are moving to this aromatic ring, yeah?
Yeah. So now we have to switch from toxic. You remember, yeah, toxic we used for this part to go from methyl group to the inside of molecule. Now we have to go to Hmbc because this C10 has no protons, so we won't see any correlations in toxic. But with Hmbc, so this is correlations over multiple bonds that connects proton and carbon. So what we can do, we can go to Hmbc and check, let's say this 1.84, because this is CH, it's a bit further away, but still we expect to see it because these 3 bond correlations are usually the strongest in Hmbc. So if we connect from H12 to C11, C10, this is like 3 bonds away. So we expect to see correlation for this proton. What we will do, maybe I will enlarge this region here. This is a bit more, but anyway, it doesn't matter. So what we are checking now is, so this, let's say with this signal here, 184, we see some correlations here that we already know. So we know the carbon at 22 and at 45. These two we already know, and they are part of this chain, so CH2, CH, and so on. But what we are mostly interested is this one here, yeah. So around 140.
And if you remember from the presentation, the aromatic carbons are, let's say, between, I don't know, 130 to 150 or something in this, somewhere in this region. So this is the right chemical shift also from this point of view. Yeah.
Mm-hmm. Okay, so this 140 is the only one that we see from this proton, and this is the closest in this aromatic ring. So it's most likely this C10. So what is additional proof that this is probably the correct one is if we look the intensity in carbon, yeah? Maybe we can just switch there. So at 140, let's check in carbon. And in this region, let's enlarge it a bit. So this is 140.87. So yeah, additional proof, we have this carbon has lower intensity than, let's say, this two here. So this is usually the case when we have like quaternary carbon, that is that one here. So C10 has no proton attached, and that's why the intensity is a bit lower. So we didn't talk much about this, but maybe now is the time. So the usual way that carbon spectra are recorded is to use decoupling through whole sequence. And this means that protonated carbons will have higher intensity due to transfer of NOE. We didn't talk much about NOE now, maybe you had it in the morning. Yeah, if you decouple, so use some power to eliminate protons, some of this saturation or some of this power will be transferred to the intensity of carbons, and that's why the protonated carbons usually have higher intensity in carbon spectrum. So 140 is the one, it is this C10.
Maybe we can just check in HSQC that this 140 doesn't give any signal in HSQC, yeah?
Yeah, that's also true. Yeah, it's again, we have multiple options to do this. Yeah, Primož said HSQC. We can go to HSQC and maybe even enlarge if we are looking in this part. So in this part here, we see just signals here, yeah, and yeah, in this case, nothing for these two signals at 137 and 140. This is one way. The other is also depth, if you remember from before. So we said there is no signals above 130. So these are actually the missing signals are quaternary carbons. And if we continue, maybe so go back to Hmbc, to the same this region that we were observing before. So the other one that we had is 2.44, and we can again see these correlations that we already knew. And then we have two more interesting here in aromatic region. So one is this 140. So even also this CH2 gives coloration to this C10, and then we have one more at 129. So this is probably the next one because it's 3 bonds away. Yeah. So the next one is the carbon here at position. Yeah, it's symmetric. Yeah. So C7 or C8, they both have probably the same chemical shift. Yeah, this is probably also thing we didn't talk about. If you have like a symmetrical part of molecule in NMR, you can see usually just one signal. If you have some local differences, maybe you can see then also multiple signal, like two signals. But in this case, if it's like free rotation and symmetrical, yeah, you will see just one. So for both C7 and C8, we see the same signal here. And if you check in carbon, so 129.4 is the signal that we were looking now. Yeah, just one more thing, if we compare the full carbon spectra, you can also see that these carbons are quite high in intensity, like maybe something similar to these metal groups. So what will tell us this? This will also mean that you have like two signals probably there and not just one. So the ratio between these two is not just protonated and non-protonated, but we also have like two carbons here because of symmetrical properties for this part of molecule.
And now we are still missing the protons, yeah, the chemical shift of the protons for
yeah, we can
H788, yeah.
Yeah, we can go back here where we left with this HSQC. So we can see now we have like two signals in this region. So the one at 129 is the one that has a bit lower chemical shift in proton. So the right part let's say the right part or the lower value at around at this aromatic region is this H7, H8. So 7.1, sorry. And this will also identify the other one. So 7.21 is its neighbor. So this is H6, H9. So again, we have like symmetrical properties. So this 7.21, and if you go back to HSQC, so we have the one at 126.27 should be the other one. And in carbon, we can get the exact number. So 127.28.
So now we have the next carbon, which is also quaternary, yeah? Number 5, yeah? And again, the easiest way to get this one, it's using this Hmbc. So you can see it at this point that Hmbc, it's very useful experiment in for structural determination of this kind of molecules. Yeah.
Yeah, here we have so one of these aromatic protons has correlation to C10, the other has to C5. Okay, C10, let's say that, I mean, yeah, we already know it's around 140. So obviously the other one has to be C5. So if we wouldn't know, so how to know which is the one? Usually, as I said, 3 bond correlation are stronger, and you will probably see like 99% of them. So you can expect that 3 bond correlations you will always see, but this is not true for 2 bonds, even if this is maybe strange in a way because it's like 3 bonds, it's further away than 2 bonds, but these are this is due to coupling constants, and sometimes coupling constant is around 0, and then therefore you will not see correlation even if it's like just 2 bonds away, at 0 or very close to 0. So usually 3 bonds correlations are strongest, and that's why. So this is like we said, this is I think C7, H7, H8 with the lower number. Yeah, and that's why we have like 3 bond correlation, which is from this 7 or 8 to C5. It's 3 bonds away. And in this example here, so where we have this aromatic ring, it's actually we don't see 2 bond correlation, but just 3 bonds correlations. So for either pair of them. So for the other one, so this at 7.21, which we said it's H6, H9, has correlation just to C10. So C5, we check in carbon, we have at 136.97. Then we can go back to Hmbc, and we can find out the other part of molecule here. So what we can do, we can there is again multiple options. We can check what is missing or what we didn't assign so far, or we can go from this C5. We set it's at 136. So we can see here is one signal to this 136, and here we have another one. So actually, both of these groups, so one is CH3, one is CH, both of these protons have correlation to this C5.
So yeah, these are then this CH number 3 and CH3 number 4, yeah?
Mm. Yeah, even if you go now to just to proton, we will see that ratio between these two, it's quite obvious. So this one at 3.70, so this is quartet, integrates for 1, so probably CH, and then at this at 1.49, it's doublet and integrates for 3. So multiplicity is it's okay. I mean, it's consistent. Integral values are consistent. So these two signals are the last two of these CHs that we were that we need to assign. And if we have protons, we can go for carbons in HSQC, or again the missing one, because we will run out of carbons soon. So the other one at 45 or something is the positive one is CH, and the other is below 20, so 17.9 is this metal group. So we can go to carbon to do both at the same time. So 44.93, we have C3, and then 18.1 and 0.10 is the metal group.
Yeah, now we are missing only the last carbon atom marked with number 2, yeah? This one which belongs to this carboxylic group, yeah? And also from chemical shift, this carboxylic, carbonylic carbon atoms are very high with chemical shift. So we can see it here on the screen that the highest chemical shift it's at 180.72. So this one for sure belongs to this carbon marked with number 2. So also if you get some unknown, if you get a spectrum for carbon spectrum from the beginning, and if you don't know much about the structure, and if you see some signals around 180, you can immediately say that these signals belong to some carbonylic or something like that carbon atoms. Yeah. So this one is the last one. So 180.72. So yeah, with these experiments, we showed you that how you can do assignment of such small molecule like ibuprofen, and maybe we have maybe still 10 minutes. So maybe we can move. Maybe we can just show you maybe this number 5. Yeah. So DNA oligonucleotide, this nosy. We can just take a quick look of this nosy. So this is. I will just, Damian, you will load, or we can do it together, and then I will just show it. This is this number 5 DNA oligonucleotide, and we just fit, and then just open. Here we will just see how it looks like a nosy spectrum of one DNA oligonucleotide, and the nosy spectrum, it's one of the most important Nmr spectrum in structural determination of these larger biomacromolecules, since you get the distances between. This is just the upper one is the trace, yeah. But yeah, this doesn't matter. So here you can see how it looks like the nosy of this DNA oligonucleotide. You can see like in every nosy that here we have proton dimension in this in both dimensions it's a proton, and you can see a diagonal like Damian mentioned before. This diagonal means that this is the same as the normal proton Nmr spectrum, and then you get out the signals which are outside the diagonal. But in the case of nosy spectrum, these signals are not due to the proximity through bonds, but they are due to, since they're protons close in space, like I mentioned in the presentation. So maybe we can just zoom it. Yeah, maybe this region here, Damian. Yeah, you can just zoom it here, or no, maybe just zoom it also with the diagonal. Yeah, a little bit. Just no, go up
So?
on the right. Yeah, like that. Yeah. Okay, good. And we can see that, for instance, these signals, just go to one signal. For instance, this signal here connects two protons on the diagonal. Yeah, just show it. This one at 8.19 and this one at 5.8, and this means that this signal is since those two protons at 8.19 and 5.8, they're close in space. They can so it doesn't matter how many bonds is between them, but it's matter that they are close in space. This means 5 angstrom apart. So maybe I will just share my screen now. Just stop sharing, Damian. I will just wait a second. I will just show this slide, which you have it, also. Sorry. Okay, now you can see it. So yeah, this is a noses, and here at the top, I will just put it like that. Okay. Yeah, this is from the same nosy spectrum as we have it now in Mestre Nova. So we can see also this region which Damian zoomed it, but I just wanted to show you here. Maybe it's easier. So we have this oligonucleotide, which means that we have this uracil, then guanine, this guanine residue, another guanine, then another one. So all the oligonucleotide sequence is U, G4, then T. So it means uracil, guanine, thymine. So 4 such strands comes together and they form this kind of structures. But what I wanted to show you, that if you do this, I think that in the morning you heard about this sequential walk, and this sequential walk can be done in this nosy spectrum in this region, where in this region, as you remember here, they resonate these aromatic protons. So they're between 7 and approximately 8 ppms. And in this region, between 6 point something and 5 point something, they resonate these protons, these so-called H1 protons of these sugar moieties. And if we take a look, this uracil, guanine. So if we take this part, you can see, and if we follow this red line, this proton, this is proton from uracil, this is aromatic proton. We'll see it's close in space to its own H1 proton, and this H1 proton is close in space to the neighboring, to the next one, to the aromatic proton of this G2, and this G2 proton is close in space to its own H1 proton, and this H1 proton is close to the next aromatic proton of G3. And Damian, I'm not muted. Huh? I'm not muted, yeah? Or I'm...
No.
Okay. And then this proton is again close to its own, and so on. And if you take a look how this looks like in NMR spectrum, this is this nosy, which we also have it on the screen. We can see that I will just tell you now that this signal belongs to this first connection between from this aromatic proton to this one, to this H1 prime. So if we follow, we can see, you can just do it like that then you just follow in line to the next peak. So this peak belongs to this distance, yeah? And then this peak belongs to this distance here. And then we go further. We just go left and then down. And this signal belongs to the distance between this and this proton here. And then again, in this here, we will go right to this signal here in the line. And this signal here belongs to another distance, and so on and so on. So you can just do it like that, going left, right, up and down. And at the end, you finish with this signal, and this signal, I don't have it written here, but this signal belongs to the distance between H6 and H1 prime of the last residue. So with that, if the molecule is, you cannot do in every molecule like this, because sometimes there can be some interruptions and so on. But this is, in this case, we can follow it from 5' till 3' end of the molecule. So you can see all these distances between these protons. So I'll just stop it here. So I hope that with Damian we were able to show you a little bit what you can do with NMR in liquids. We just show you the basic things, how the assignment of the small molecules can be done. But there are many more things in the case of bigger molecules, from proteins, from structural determination of proteins, nucleic acids. These are DNA, RNA molecules, and also in the case of proteins, if you are working with quite large proteins, your sample should also be for structural determination. It's good if they are 13C and 15N labeled, as well as in some cases, due to relaxation, if they're quite huge, they should also be deuterated. So these are some points which I wanted to tell you. So if you have any further questions about NMR and what we can do, you can just contact us, and you can also contact us through CERIC proposals. And yeah, okay, yeah. If you have any questions, just ask. Yeah.